Find the energy of a given sequence in time domain and frequency domain. The given sequence is x of n equal to 3, 4, 5, 1, 2, 3. We want to calculate the energy of a signal in both time domain and frequency domain. This will also help us confirm that the energy is the same in both domains as per Parsel's theorem. So basically we are proving Parsel's theorem. So before going to the code, let's go through what is Parsel's theorem and energy in both domains. Energy of a signal is a measure of its power over time or frequency. For a discrete signal x of n, we calculate the energy as the sum of squares of its value. Summation n equal to 0 to n minus 1 x of n whole square, where n is the total number of samples in x of n. So this is the equation to find the energy in time domain, and energy in frequency domain is represented as capital X of k, which is the result of f of t on x of n. The energy frequency is given by 1 by n summation k is equal to 0 to n minus 1 x of k the whole square. Here n is the total number of samples, and Parsel's theorem states that the energy in time domain is equal to the energy in frequency domain, which is summation n is equal to 0 n minus 1 x of n the whole square. This is the energy in time domain, which is equal to 1 by n summation k is equal to 0 to n minus 1 x of k the whole square, and this is the energy in frequency domain. We have to prove our energy in time domain is equal to energy in frequency domain. So now let's go through the code. Here we are importing a library function numpy, and next we are going to define our array x equal to np dot Here we have defined a signal x as an array of 6 numbers. Now we are going to calculate energy in time domain. Energy in time domain is given by np.abs. This function takes the absolute value of each element in array x. Okay. In x 3, 4, 5, 1, 2, 3. The absolute value is simply the value itself, since all elements are already positive. So the result of np.abs of x would be 3, 4, 5, 1, 2, 3 itself. And np.abs x double star 2. Here this double star 2 squares each element of x, which gives the magnitude square of each element. 3 square, 4 square, 5 square, 1 square, 2 square, 3 square. np.sum. np.sum calculates the sum of squared values from the previous step. 3 square, 4 square, 5 square, 1 square, 2 square, 3 square. And what will be the answer? Which is 64. Okay. Energy in time domain is 64. Okay. Now we have already calculated the energy in time domain. So let's calculate energy in frequency domain. Capital X is equal to np.f of t dot. We transform our signal from time domain to frequency domain using fast Fourier transform f of t. This gives us the same signal but represented by its frequency components. So here in capital X we save the f of t of this small x. The result capital X is a complex array representing the signal in frequency domain. Next we are going to calculate the energy in frequency domain. So we know how to find energy in frequency domain. This is the equation to find the energy in frequency domain. X of k. This is the result of f of t on x of n. We know that. Now, what is the equation to find frequency domain energy? 1 by n summation k is equal to 0 to n minus 1 x of k the whole square. This both equation is almost same except this 1 by n. So, in this step, we calculate the magnitude squared of each component and sum these values and divide it by n. And print the energy in frequency domain. According to Parsel's theorem, the total energy in time domain should be equal to total energy in frequency domain. So let's check if our energy in frequency domain is same as energy in time domain. Yes, energy in time domain is 64, energy in frequency domain is 64. Hence, Parsel's theorem is proved.